Alright, so welcome to Unit 2 on transmission lines. So in Unit 1 we covered aspects that were probably taught to you in high school. It was hopefully a good refresher of how circuit elements were modeled and what were the underlying assumptions while uh, deriving relationships between the terminal voltage and terminal current for some simple basic circuit elements, right? And we identified that there was perhaps something missing, right? Especially when we look at uh, fast time varying or rapidly time varying voltages and currents, we notice that we are seeing behaviors in practice that cannot be quite simply explained by those toy models, right? So we are now going to start a journey in trying to establish the understanding of high frequency circuit behaviors, right? And as a first stepping stone, rather than addressing the elements of resistor, capacitor and inductors, we actually go even more simpler. We say that we would like to understand the role of wires, simple wires, connecting wires within the circuit when we start going to very high frequencies, right? And now that we understand that voltages and currents are the effects, right, and the cause is the underlying electric and magnetic fields, it is important to study voltages and currents always from the view or the perspective of the fields, right. So always evaluation of the fields comes first, and the repercussions or the impact of these fields seems to be in generating voltages and currents within the circuits, right. So the cause and effect has been quite simply established between the fields and the observable quantities like voltage and currents, right. Because another way to think of it is you don't very readily find in labs, even in your college, tools to measure fields, right. So you have something called the digital multimeter, which will only provide voltages and measurements of currents, right. So you might even have seen a current meter, right. So voltages and currents are ones that we are familiar with in the lab as a circuit designer. Even when I make my final circuits and I have them running in my lab, voltages and currents are the ones that are more tangible and the ones that I can readily find equipments to measure, right. Fields, on the other hand, are more of a concept, and I don't think we find as many equipment that try to measure fields themselves, right, because it can be a quite arduous and challenging task. Okay, so we do need the viewpoint of currents and voltages in circuits, but we have to go with the understanding that the fields are the ones that are generating these voltages and currents, right. So in order to be able to design new circuits, I perhaps need to have the field picture in mind before I can go to constructing the actual circuit, right. So in this course on transmission lines, we are going to study the impact of current carrying wires in high frequency circuits, and we call them transmission lines. Okay. In your circuit theory that you've been taught so far, there was perhaps no emphasis laid on the physical size of the circuit, right. Be it the circuit shown in 1 or in 2, you may say that the ultimate dynamics and the currents and voltages I calculate is irrespective of how I draw it, right. I could have even drawn a minuscule version of this circuit. It's really the values of the resistors and the voltages from the voltage source that dictate the potentials at every point along the circuit, right. And that just inserting pieces of wire does not really alter the final solution, right. So we had that kind of a notion, and we perhaps should try to revisit that notion, right? For a simple reason that we would like to see the circuits in the viewpoint of fields, right? And also remember that I introduced the idea that there is perhaps more reason to study fields and hence the generation of currents and voltages for high frequency circuits, right? So, especially when things are fluctuating very fast. So, now we are going to try and quantify what fast means and when do I have to worry about transmission line effects when I am looking to study circuits, right, or even designing circuits. So, we often use the idea of transmission line theory whenever we want to indicate that we care about the speed of light delay, right. So, we know that when a particular charge or a charge is set in motion in a particular location, the activities of this charge does not permeate the universe instantaneously, right, and a particular location further away from the charge only receives the message of what the charge is doing some time prior, right, and this time is essentially the distance between these 2 points in question divided by the speed of light, right. So, this is what we mean by saying that we say that the speed of light delay is no longer insignificant, right. So, we are looking at circuits with dimensions where the dimension of the circuit is a significant fraction of something called the signal wavelength, right. So, the signal wavelength comes from the popular relation C equals lambda f, where f is the frequency of your voltage source or current source, and using the speed of light we can estimate so called signal wavelength, right. So, now this is the dimension in question, right, and we are going to compare the circuit sizes that we are building to this lambda or signal wavelength, and we are going to ask ourselves the question, is the circuit size a considerable fraction of this wavelength, right. If I say or if I find out that the circuit has a size that is in the order of lambda or maybe even larger than lambda in some cases, then transmission line effects are important to consider, right. The so called retardation effect between the cause and effect needs to be considered, right, in order to explain the phenomena or the behavior of this circuit, right. So, the rule of thumb is to say that there is a rough fraction of 1/10, right. So, if my circuit is bigger than 1/10 of the signal wavelength, then I say that transmission line effects can play a significant role in changing the behaviors of your circuit elements from what you expect in the case when you neglect the speed of light delay. So, this transmission line is essentially a pair of wires, right. So, I have shown this as a wire wrapped around with another conductor. So, when this voltage source is trying to drive a current through this circuit, it follows the central conductor to the load, and the return current from the load comes back through the outer cylinder and back to the source, right. So, I need 2 wires to essentially take current to the load and bring it back from the load, okay. So, these 2 conductors in conjunction is called a transmission line, okay. So, now the question is, how do we model this wire, pair of wires, right. So first we need to know what is this pair of wires doing, right? So recall back to the very first video in the introduction where I motivated you for by showing you some real world examples of circuits that don't seem to fit into our traditional notion of circuits, where I said that when I was simply trying to communicate a piece of information as a voltage waveform from the driver to the receiver, even though I just have a simple conducting copper trace marked by the red trace that I just drew, I noticed that the shape of the voltage waveform at the beginning of this trace and the end of the trace looked very different, right? And we said that the signal seems to have stretched a little bit. It has also shifted in time, of course. This is the speed of light delay that we talked about. And then it has also been scaled, so its height seems to have been reduced, right? So we have to somehow explain all of these phenomena that seems to be happening to the waveform that was launched into these pair of conducting wires, which we call transmission lines, right? So let us start to making a model for this, starting from the construction of some of these cables, right? So let us start with the cable that I used in the capacitor resistor example, right? So I had this kind of a cable. It's called a coaxial cable. I use this cable to essentially connect between the breadboard and to the voltage source, right? And if I look at the construction of this cable, there is a central conducting wire, and although it looks like two separate conductors on the top and bottom, because this is a cross section of this cable, right? So I basically cut across this cable and I look at this cross section. It seems to show that there are two conductors, one on the top and the bottom. It is actually part of the same piece of conductor that seems to be wrapping around the signal. So this is what we call a coaxial cable, because the outer conductor, which is bringing the return current from the load, is symmetrically wrapped around the signal conductor in the middle, right? So when I see such a construction or a geometry, what I notice is there are two pieces of metal and they seem to be separated by some kind of a dielectric to not collapse onto each other and create a short circuit, right? So this reminds me of the capacitors, right? So perhaps this cable requires capacitors, right? So now I am going to try to make a distinction, right? So when I am saying that I need to make a model of something in the real world, I am actually going to use resistors, capacitors and inductors, but these are used in the idea that they are of their ideal form, right? So I am going to use ideal inductors, capacitors and resistors to model the behavior of something that is real, right? So try not to get confused and question yourself saying that we are using capacitors and inductors in this model, and is it still plagued by the same issues that we saw when we derived the relationships between I and V for these capacitors and inductors even in the model? Not so, right? Remember that we are doing the other way around. I am not taking a capacitor and asking the questions what does its behavior look like, but instead I am asking the question, how can I model the behavior of fields around this pair of wires using ideal circuit elements, right? So that is the journey that I want to start right now. And the reason for this journey is quite simply that I still want to remain in the realm of currents and voltages for two reasons. One, it largely reduces the complexity or the dimensionality of the problem. electric and magnetic fields would require me to work with 6 different variables and over 3-dimensional space and time, right? Whereas I am going to reduce the complexity by considering I and V, and also that I and V are really what I can measure in the lab, right? So I have equipments that are designed to measure voltages and currents, right? So I am going to use ideal circuit elements to mimic the behavior of a real construction, right? Which in this case is simply a pair of wires, and I am going to start by saying that maybe because the conductivity of these wires is finite, they are not superconductors, that there will be some series resistance, and because there is a geometry showing there is a separation between two metal conductors, I am going to bring in a capacitor between these two lines, right. So I am going to represent this transmission line as a ideal circuit containing a resistor to represent the resistance of the wire and a C wire to represent the capacitance between the two wires. This capacitance is essentially a stand-in for the electric field that is established between the two wires, right. And although this may seem very crude and very hasty, this is a very popular model, toy model for digital design, right. So when you create a chip, a CMOS chip, and you have interconnects going from one transistor to another, you very often use this so-called RC delay model, right. And it's actually able to do quite well in predicting the delays of the interconnects to some very high degree, right. And you can actually, instead of lumping the resistor and capacitor and bringing out to be a single element, you can also divide them up, right, into what is known as the pi and t models, where you distribute the capacitances to the input or the output or the resistances, and they do a better job of fitting. And even better thing that you could do is remember that these are not lumped elements, right. So the interconnect that you have, the transmission line, the resistance is sort of distributed all along the transmission line, right. It is not that all the resistance is lumped at the input or the output. So this distributed nature could probably be modeled by taking several of such RC pairs and stacking them one after the other, right. That is what the second bullet is saying, that instead of just a single RC, I could have a bunch of them, right. And these happen to be slightly better than having to lump them into a single resistor and a capacitor, right. Okay, so we don't want to stop here. We notice that this simple model doesn't carry us too far outside the realm of digital design. So we want to get some more insight, right. So one thing we know is there are magnetic fields around current carrying conductors, right. And when I look at a particular situation, say I have a current source and I have shorted the other side of the transmission line, I end up having this current traversing through a fairly large loop, right. And the magnetic fields, right, that loop around each of these conductors are breaching this large hashed area, right. And the area that is indicated in the hash can be quite large for long transmission lines, right. Again, the word long should be thought of in with respect to the signal wavelength lambda, right. So now when the currents are changing with time, I have a rather large amount of change in magnetic flux, right, because the sheer area that there is compounds with the length of the transmission line. I have some significant flux, magnetic flux, and this time rate of change of flux can actually introduce local electric fields, right. So to mimic this behavior, it looks like I need an inductor, right? So in an inductor is where we saw that time rate of change of magnetic fields causes this electric field, and we want to incorporate that inductor as an element in this model, right? And the open line, of course, the situation tells us that we need a capacitance as well. So now with this new insight, let us see what we can do, right? So what we essentially say is that this transmission line of some length L can be broken down into pieces, sub pieces delta x, where each delta x region constitutes a circuit, right? A circuit that consists of inductors, capacitors and resistors. But you may notice that I have brought them, the value of these inductors and resistors seem to have been introduced with the delta x, the spatial dimension, right? So the L, C, G and R that you see no longer have the units of Henrys, Farads, Siemens or ohms, right? But rather are distributed quantities, right? Remember, this is only a representation. So we say that L is the inductance per unit length, right? So L stands for the inductance per unit length. Similarly, C is capacitance per unit length. G is Siemens per unit length, and resistance is ohms per unit length, right? And if I want to get the value of the inductance, the resistance or the capacitance, I need to multiply these numbers by the delta x in order to get the value of the inductance, right? So if I have a 1 nanofarad per meter cable, and if I give you a 1 meter cable, the net capacitance that I would measure between the central conductor and the outer conductor would be 1 nanofarad, right? So again, what should be the delta x I choose? Now I have to go back to my rule of thumb. So this delta x needs to be sufficiently small compared to the wavelength, right? So L can be comparable to lambda, but delta x has to be much smaller than lambda, right? So the rule of thumb said 1/10, so you could do something better than that. So you can divvy up your length L into subsections that are all less than 1/10 of lambda, and you can substitute each of these sections with this ideal elements, and you can say that this is what the net effect of introducing a transmission line or a pair of conductors of some finite length that is comparable to the wavelength of the signal, and the effect that it has on the circuit performance, right? So this is how I can model it. So you could perhaps say that this is perhaps the end of transmission lines, right? So I can just go ahead, go to a simulator, fancy software that basically does lots of complicated circuit analysis, and you replace the transmission lines with these ideal elements, and you have as many as you want, and put in enough computing resources, and you can out pops the currents and voltages, right? But instead we can go a little bit further, right? Because these circuit elements that we have chosen, the delta x's we can say are the same, and so L delta x and R delta x, these values of inductors and resistors, these individual blocks are identical, right? So we will try to see if we can go the analytical route, right, and try to actually see if we can get a closed form solution for currents and voltages, and then you may not require to actually break this apart into subsections and actually painfully model them in circuit simulators, right? And before we start on that, I just want to leave this slide by saying that this is no special arrangement of inductors, resistors and capacitors. You can of course might have even rearranged them like the pi or the T model or any of these that you see on the right. This should not significantly distort the IV relations that we are going to come up with, right? So before we take up the entirety of that distributed model and try to solve that, which in itself can be quite cumbersome, we take a simpler exercise case just to highlight the difference from the kind of IV equations that you are used to the kind of IV equations that we have with transmission lines. So, we say that let us assume ideal conductors. So, there is no resistances or leakages between these two conductors through the dielectric that is separating them. So, we only have the inductive and capacitive elements to represent the magnetic and electric fields and the interplay between them, right. And we say that one particular segment has a input terminal voltage and current, that is V and I, and an output terminal voltage and current that has incrementally changed to V plus delta V and I plus delta I, right. So, now using the ideal circuit equations, right, remember that we are only trying to model them with ideal circuit elements. We can write expressions, right. So, this is your famous V equals L di by dt, and this is your I SC dV by dt. But now these inductors and capacitors are dependent on the length, right, because they are the distributed values, right. So, these equations are showing up in the new situation as the ones written in black, right. And if we rearrange this delta x to the left hand side, we actually notice for the first time that we have a spatial variation. We allow for or accommodate for a spatial variation in voltage and current along a conductor, right. So, this was not true. Remember that when there are no resistances, we assume that I and I plus delta I are the same, right, and V and V plus delta V are the same, right. For the first time, we are noticing that between the input section and the output section of this very tiny element, we are allowing for the voltages and currents to be different, right, despite there being no resistors. Okay, so this is a first leap in understanding of high frequency circuits and modeling of transmission lines, okay, where spatial dimension seems to enter circuit theory. Okay, before you were simply happy with time being the only variable and establishing currents and voltages for all times at different parts of the circuit. For the first time, we are actually saying that we are also allowing for voltages and currents to be different at different locations on even an ideal conductor, right. When does this happen? This happens when the rate at which I am fluctuating the voltages and currents at the source are extremely rapid, right, and the sense of rapid comes from the speed of light delay when compared to the time period of your source, right. And the time delay, the speed of light delay between the source and the load is significant fraction of the period of your voltage or current, then we notice that we should allow for voltages and currents to be functions of space dimension, right. But nevertheless, this is still less cumbersome than using electric and magnetic fields, because we have only used one spatial dimension, not three, right. So, this is still convenient, and it is a very good stepping stone for us to deal with the complete three-dimensional picture of the fields. And what is interesting to look at these equations is the inherent cycling, right. We said that changing electric fields cause magnetic fields and changing magnetic fields cause electric fields. This cyclic phenomenon seems to be present in this equations that we see, right, because time rate of change of current is leading to changes in voltage, and time rate of change of voltage is leading to changes in current, right. So, in some sense, this should remind you of the cyclic behavior between fields of electric and magnetic nature, and somehow that parallel is being brought over to voltages and currents. Okay, so at this point, we will say that we are ready to now solve these equations and try to see if we can come up with closed form solutions for currents and voltages. Some of you at this point might be a bit concerned, saying that the way we have been modeling these transmission lines seems very ad hoc, right? So we try to get some insights by looking at the geometry of these transmission lines, and we incorporated ideal elements. What is to say that there may be more elements than we have considered, right? Why are you not actually, even though you've said that the fields are the ones that are truly controlling these voltages and currents, why have we not dealt these transmission lines with fields and rather seem to be stuck with these currents and voltages? To give you some satisfaction that we are actually on the right track, in the next section, I will actually derive these same set of equations using the Maxwell's equations as well, just to give you some assurance that these circuit models that we come up with is completely encompassing all the effects that we expect to see from the fields, right? And then we will go on to studying more complex behaviors of just the transmission line and conclude this unit after that. Okay, thank you.